Okay, so let's have a look at chapter 12, differentiation. It's quite a big chapter here, and a lot of this will be brand new for you if you didn't do any additional mathematics at GCSE. It's also, one of the best chapters, in my opinion, where you sort of learn one of the most useful tools. Many different sections here. It's all related to gradients, okay? Gradients of lines and all the different things that you can actually work out from this. So if we talk about gradient, you might start thinking about a straight line straight away. And we learned that with a straight line, you just sort of pluck the coefficient of x, and that's your gradient. Okay, but where did that actually come from? It came from the sort of the change in y divided by the change in x, and that's going to be important because we're going to see something like this a little bit later. The problem with this, though, is this only works for straight lines. If you look at what's here on the board, if you look at all these black tangents that have been drawn, they clearly have different gradients. That one, for example, has a negative gradient. That one there's 0. This one here is positive. So the gradients might be something like this. So that might be -6 and -4. When in fact, that's actually what these things are, but I'll tell you how we're working this out later. But you can see there's all kinds of different gradients. So just kind of by looking at patterns, what's the connection between this and how we are using our x values to get these gradients? How are we finding these here? There's a simple connection you might see, but you're not sure why it works at the moment. And what it is at any point, if you take the x value and you multiply it by 2, that's going to give you the gradient. And that is true. That's also true, by the way, for other points that are not drawn on here. But we don't really know why this is happening yet. But the key idea is that different to a straight line that only had one gradient value, okay, the gradient value here depends on what the x part of the coordinate is. So if we wanted to find the gradient, we might want to link it back to a straight line to start with. So when we had a straight line, one thing that we could do is we could look at the values and we could draw a small right angle triangle. This is x squared. So if you put x equals 5 in, you get 25. And if you put 6 in, you get 36. And you could draw a triangle from this. This is much steeper than it looks in the diagram. Well, the difference in y values is 11, and the difference in x values is 1. So the gradient of that tangent that I've just drawn there, it's not really actually a tangent. This is called a secant line, like a cutting line. But you can see this sort of like approximation that I've drawn there would have a gradient of 11. The difference in y's over the difference in x's. But that's not perfect. That's not really the answer, is it? Because it's not a tangent and it's between these points. So it's a little bit clumsy. So you might want to move these points closer to each other, like over here. So instead of 5 and 6, you've got 5 and 5.01. So they're very, very close to each other. And you see the black line there is more like a tangent. This wasn't very good over here. This is, this is pretty good. What would the y value be there? Well, if it's still x squared, you just square it. And difference in y over difference in x, chuck this in a calculator, and you get 10.01. So it's definitely different to 11, 10.01, which is pretty good. The real answer, by the way, is 10. So if you make the gap between them, if you make the x gap between them, the difference in x, very, very small, you'll get a very close answer. So let's be a bit more formal about it now. What we're going to do is we're going to pick in general a point x. So we're just calling it x now instead of giving it a number. And for the other one, we're going to go across a little bit. I'm going to call this distance h. So the x value of the blue dot is x plus h. So whatever it was from before, and you add on h. To find the y values, you just plug them in the equation up here. So if x is the x part of the coordinate, then the y part is x squared. That's another way you could write it. What if you put x plus h in? Well, you'd get x plus h squared, wouldn't you? Okay. So we're going to use this here, and there's something very similar to this in the formula booklet, by the way. Okay. We're going to use this, and we're going to do the difference in y's over the difference in x. So the difference in y is this x plus h squared bit here, take away this bit here. These are the two y's. Okay. Now this might put you off a little bit, but this is important here if we really want to understand what's going on. What we're going to do is we're going to use limits, which is a tool that you don't use very much in A-level maths, but it is important here for the theory of what's going on. We're going to say that we want the gap between them. Remember, this h distance is the x coordinate gap. We want this to be very, very close to 0. Not 0, but just very, very, very close. Okay. And what else do we have? Well, the top line is still the difference in y values. Okay. The difference in x values, well, we said from before that h, or if you prefer, x plus h minus x is also h. So you could do that as well if you prefer. So, if you wanted to think of it this way and say, why is it not this? Well, it is. Okay. So what happens here? What happens here if we keep working with this? So x plus h squared, you could expand that, and maybe you could clean things up a little bit. Well, if you do x plus h squared, you'll get x squared plus 2xh plus h squared, and then there's a minus x squared at the end. And what they've done is they've cancelled that, which leaves you with this part here. The limit notation, this bit here, you just keep this on going throughout. What else can you do? Well, you could factorize h from the top, and you would get 2x plus h over h. And when you have a common factor throughout numerator and denominator, you can cancel those as well. And here's the clever bit. Because we've sort of manipulated this and worked through, and we've kept this limit part here, now we can use this limit part. So you end up with 2x plus h, but we said we want h to be like very, 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 very close towards 0. When it gets towards it, when it's right next to 0, well, it effectively is 0. So that bit sort of disappears. And what we've said then is the gradient is not just a number. The gradient, there is a rule now to find the gradient. It's not as simple as saying the gradient is 4, the gradient is 5. It depends on the x value. So this is the gradient function. So for example, if you want to know the gradient when x equals 1, you would do 2 times 1, it would be 2. If you wanted the gradient when x is 5, it would be 2 multiplied by 5, it would be 10. And this is the 2x that we saw from earlier. This is called differentiation by first principles. So you're sort of understanding the idea behind it. In the formula booklet, it appears much more like this. So the gradient function is often shown by f dash x or dy dx. Remember, we said difference in y over difference in x. Okay, this is delta, and that d there is delta. So they're the same thing. And you do sort of like your larger y value when you plug that inside the function minus the y value from the smaller, if you want to think of it that way, divided by the difference in x. Well, the difference in x is that h gap between them. So something just like this appears in your formula booklet. There's different notations for it as well, but often you will write it like this, or like this. So let's do another example for you. Let's do a quick sketch as well to start with. Y equals x squared. So the point 416 lies on there. Well, of course it does, because 4 squared is 16. So 416. At point A, so also at this A, the curve has a gradient. So if I wanted to find the gradient, I was thinking of it sort of like a straight line. Okay, I need a triangle from my difference in y over my difference in x. So let's sort of mark this point over here. And how much further along is this? Well, it's h further along. You're going to do 4 plus h. Okay. In fact, 4 plus h, yeah, I'm going to use that because look, there's no x, so I'm going to use the number. So it'd be 4 plus h. And if you wanted the y part, you have to do whatever that is, squared. So if I do difference in y over difference in x, what do I get? So let's write that out. So we write sort of the bit with the h in the y part first. So difference in y over difference in x equals. Remember, we're going to say that h is a very, very small distance. In fact, we're going to use that notation there. So the limit as h goes to 0 is, what's the difference in y? It's whatever 4 plus h squared is. That's the y value of this bigger part here. And then the y value of the smaller part, which is 16. The gap between them is h. So I'm just going to jump straight to that. So that's the same as the limit for h goes to 0. Let's expand this out. We're going to get 16 plus 8h plus h squared minus 16 over h. And the 16s cancel. You could, if you're happy to as well, while we're at it, we could take an h out of everything here. So we could, as long as it's clearly visible what you're doing, write this. So the limit as h goes to 0, well, it's 8 plus h, which is what they were asking us for here. Show that g equals blah, 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 blah. G is, they've just given it a letter, this equation. Deduce the value of g. Well, as h goes to 0, this part here will disappear. So for part B, it's just 8. Yeah, the gradient of that part there will be 8 if you drew a tangent exactly at that point. You've done something similar to this, by the way, at GCSE, when you had to draw a tangent and then use difference in y over difference in x. It's the same thing, but we're just doing it a bit more rigorously. So have a go at this one here. Bit of advice I would give you as well. You know you're going to get x plus h cubed. So you might want to use Pascal's triangle for this as a quicker way for finding out what these parts here should be. And remember, the formula is whatever the y is when you put the x plus h bit in, minus the fx bit, minus the y from the usual part over h. And don't forget, we've got a limit as h goes to 0. So pause the video, have a quick go. So I'm assuming you've done that. Let's have a look. So this is how we want to sort of set up the question. The function is all about cubing. So you could, as a first step, write this in. Then you just need the larger part minus sort of the smaller part. Expand it out. 1, 3, 3, 1 are Pascal's numbers. And these bits, you'll always find that these bits here will cancel. Don't use the h is 0 bit until the very, very end of the question as well. So h, we do some cancelling with h. And we end up with this line here. Now, because h is still there on these two parts, it's going to take these ones out because it's multiplying it by 0. This bit, however, gets left alone because h has already sort of been cancelled out here. So 3x squared is the gradient function for x cubed. In other words, if you want to know the gradient at any point of an x cubed graph, take your x value. So let's pretend this is -2, for example. Plug it in here. So 3 times -2 squared. Well, what's that going to give me? It's going to give me 412. I have a positive, so positive seems right. Yeah, the gradient at that point, that particular point, will be 12. So it's time for you to have a go. You may wish to have a go at some of these more difficult ones that perhaps have 2 parts as well, if you like.